plain old Black & Decker cordless screwdriver. How this thing works here is you have a motor here, and then you have what they call planetary gears here, and then they have the planetary gears are attached to an arm, and this is a two-stage operation. So they got two stages of planetary gears on top of each other. So in a very small package, this here actually turns out to be, and then the ring gear, which is the fixed part of the outside of the cordless screwdriver, the ring gear is stationary, but it has teeth in it. And these teeth make contact with the planetary gear teeth. The planetary gears are not touching here. They can't. It would lock up if it did. But in this right here, you get a ratio of, I think on this one here, of nearly 80-to-1 gear train value. So it's a system where you're using compound gears, but planet gears and sun gears, and I'm going to explain all that in a second. What that means is, when this thing broke for me, and I'll try to remember to bring it in next time. When this thing broke on me, I could hit the motor on this, and I see this little gear spinning. I could just take my fingers and go, beep, to stop it. Very easy to stop. But then when I put the gears all back together and turned the thing on, and I grabbed the screwdriver part, I couldn't stop that from turning. Because it's an 80-to-1 ratio. So it's got a tremendous amount of torque. So the torque was multiplied by this little motor 80 times through the gear train to give tremendous output torque on the thing. So that's the beauty of these planetary gears.
Why is there two stages?
Why is there what?
Two stages?
Because one stage was only produced 9-to-1, and they want to produce another one of almost 9-to-1. You get 9 times 9 is 81-to-1. Okay? So they weren't satisfied with just a 9-to-1 ratio. They wanted more torque. So these are called epicyclic planetary gear trains. So let's look at the definition of what epicyclic means. It's a circle whose center moves about the circumference of a larger circle. An example of this is the moon about the Earth, about the sun. So that's why we'll either call it epicyclic gear trains or simply planetary gear trains. All right. Let me draw a very simple representation of this. Okay, so this right here is the sun. And And then this one right here is the planet. Now, as you know, our sun is bigger than the planet, but normally in these systems, the sun is smaller than the planet. And then they have something that connects these two. And this is called the arm. Okay? All right, so let's look at what this is doing. All right, so what we do on this here is we're going to guess all omegas as positive. And if we guess wrong, the answer comes out to be negative, so, you know, it naturally comes out saying that we guessed wrong because it gives a negative value. So we guess all these things are going positive. So we're saying that this is going positive. We guess that this is going positive. And we guess that the arm is being driven positive.
When you said it was about the circumference of a larger circle, but then you said that in this case it usually is smaller?
Yeah, so this right here, this is moving about the center of this smaller one. And the definition, did I say larger? No. So ignore the definition. Look at the picture. So if I look at this right here, I'm just isolated on omega sun, then the pitch point here, which I'll call P, okay, so this is P. On this side of the pitch point, because omega sun, I guess that's positive, it's going like this. So this right here, rather than writing omega s times rs, I'll go ahead and make the direct substitution of the gear tooth in there. And then if I look at this side here, if I step over the pitch point and look at what this omega is, because I guess omega p going like that, I have omega p times np going like that. And I have to account for the arm also. The arm, because I guess the omega arm going up like that. And omega arm, this right here is omega arm times the radius of the sun gear, which I'll make the direct substitution of ns, plus the radius of the arm, which I'll make the substitution radius of the planet gear, which I'll make the substitution in P. Okay? So those are my equations. And then what I do here is I look at what direction I'm going to, as far as the linear velocity vectors, what direction I'm going to choose as positive and which direction as negative. I generally choose the most vectors that are going in one direction, I'll choose as the positive direction. So in this case here, any linear vector going like this, I'm going to say is a positive value. And any linear velocity vector that's going down, I'll choose as a negative value. Okay? I then write the equation at each pitch point. So at P, pitch point P, I have plus omega s times ns. And then what I do is I hop over the pitch point, and I see I have a minus omega p times np, and then a plus, because the planet is being carried, the center of the planet here is being carried by the arm. I have to say that that is plus omega arm ns plus np. Okay? Yep.
Can you explain again the downward omega p and p part?
Yeah. So, because if I just looked at this right here, okay? So I'm just focused on that. Because I guessed omega s going like that, that linear velocity vector is going straight up, okay? So then, if I cover up this part here, and because I guessed omega p going like that, this one's going to go down like that. So my rule is I'm going to guess all the omegas being positive. Because these things, when they start moving, the arm going and this is going, these things are, you can get some really strange looking motions out of these things. All right. And so because I guessed omega arm going like that, I have that one going up like that. The center of this gear going like that. Okay?
So wait, is that point, the omega s, ns, and the omega p, np, are those points on the arm though?
Yeah, that's the center of this point right here is the center of this gear where the arm is attached to that center.
I meant the omega, yeah, the omega p, np, and the omega s, ns. Those points, are those on that center or right next to it?
Right next to it. Just.
But they're on the arm?
Well, they're actually on the circumference of this circle and this circle respectively.
So they're not on the arm? Okay.
So I have this equation right here. So this equation defines what's going on with this system here. And if omega arm equals 0, so the arm is fixed, we'll say, that leads to omega p equal to minus ns over np times omega s, this being our input, this being our output. And this is a simple gear pair. All right? So when I look at this thing here, and I say, well, I'm not going to move the arm, I'm right back to the very first system that we looked at when we were talking about gears, which is a simple gear pairing. And notice by guessing all the omegas positive here, my negative sign comes up naturally. And we know that that is true because if this thing is moving, the arm is fixed, this is moving like this, then the planet will be moving in the other direction. And the negative sign shows that. Yes?
Just kind of answered there. Why don't you just guess that the omega p is going the other way?
I mean, you could.
Isn't it always going to be the other way? If one's going one way, the other's going to go the other way?
Well, what happens though, if the nice thing about guessing all of them positive, that when you get a negative answer, you go, oops, okay, I know that that one's going the other way. So if you guess them all positive, it always comes out so that when the negative occurs, you just recognize that, oh, it's going the other direction. Okay? All right, so then if we have omega s